Okay. I know this is a discussion session. Let me just test this. Yeah. Okay, I see. So this comparison that we're all thinking about now, there was a similar effort in the 90s. So I made some slides, and I put up some other slides, which I'm not presenting, but has a list of references. To tell some history of what happened between the interferometers and bars a long time ago and the comparisons. So the interesting thing is, I put everything up here. Here's an interferometer. I did spend 1 year working on interferometers in Japan on the Kagra project as a postdoc. So I did work a little bit on those. Niobe was PhD and postdoc here. But the experiments I'm working on now, we're part of ADMX. Oops. We're part of ADMX, and we're doing quite a bit of work with them. And we have these experiments, MAGE, Upload, and Organ, that are currently running experiments. And what I found interesting was, okay, got it. This paper I thought was great. When this paper came up, there's some authors in the audience. It showed that haloscopes also were gravity wave detectors, and the key point was that where you have these effective currents, which you've heard about, that the gravity wave effective current was on the order of the axion theta, what you can call theta, which is just the coupling times the field, because this is a dimensionless quantity, and so is h. So that caught my interest because I'd worked a lot on gravity waves, and I was working now on axions. So this I think is a really interesting thing that was discovered in the community by these authors. And because we're working on those, it made me go back to thinking about the difference between broadband and narrowband detectors. So here's a little bit of history of the bar detectors. We've heard a bit about Weber's pioneering work. That was way back in 1960, and if it wasn't for him, we wouldn't be here today. He was a bit of a character. I met him a few times at conferences. I can tell you stories. And I was doing my PhD on this Niobe gravitational wave detector. I moved all the way to Perth from Melbourne because a project really interested me after doing a physics degree and an electrical engineering degree. So these were all the bars in the world, and here's a few of them. So what happened? Here's a bit of a history lesson for those I want to give. Resonant bars versus interferometers, there was. We've all got these competing technologies, but back in the day there was this competing technology. And in the early 90s, interferometer technology threatened the resonant bars, and we all know that they won, you know. But the bar community had to develop the concept of this strain per root hertz to compare, because they weren't doing that beforehand. And I started in '89. It was only really in '93 when we started doing that, so I was there. And it was the LSU guys who started thinking about this, and I was going to conferences with them, and I was working it out too at the same time. And they published this paper back in 1993, where this is probably the first time I saw this, where they were talking about this sphere, and they showed that it could be better than LIGO. This was the first LIGO that they were all proposing, and they showed this. And the dashed line is an array of resonant bars, and this solid line is an array of these so-called TIGA, spherical resonant detectors. And they were looking very promising. And the conclusion was that the two types of detectors are complementary, and that each have a frequency domain where predicted sensitivities are superior. Maybe we're there today with high-frequency gravity waves too. We've got some broadband and we've got some narrowband techniques. And discussions with the LSU group led me to figure out all of this for Niobe. So this was very interesting. So what I did, it's been 30 years since this PhD was written, but I put it on the archive. It's 30 years old. It's there now. So, and we were just looking at these resonant bars, and then there's this paper which is basically the same material in the thesis, which was submitted just after I wrote my thesis and was eventually published in, it was accepted in December 94 and published in 95. And this is where we looked at the noise budget. So what we do is you have noise at every input here. And just like when you do any noise analysis, you refer everything back to the input, okay? The input is here where the gravity wave is. So we're referring all these noise sources back along the train to the input, and then you can get these figures, which are strain per root hertz, okay? And so that's basically what you do. And you can see there's noise coming in here. And in the end, you get these two sort of lumps because you've got two modes in this system. So that's what we could, now we could put on the same plot bars and interferometers. This is discussion too, so I know everyone's been butting in, so you can butt in on me as well. So in the end, if you have no noise coming in here, you can really get large bandwidth because the gravity wave signal seems the same as the thermal noise here. So inherently, if you've got no other noise sources up here, this part is broadband. And that's the point that we were working on and can be a misconception. And so we came up with ways where we think this was Niobe, how we could broaden the line width and start doing more interesting physics if we detected gravity waves. And so here's an example. This was Allegro, the LSU. This was their actually real data referred back to the input. It looked like this. Niobe was like this, and then this was from a paper where we were proposing to improve it. And here's LIGO in 2020. And we could put them on the same figure and we can understand, but it's not complete. So what you really,
Can I interrupt you just there?
Yeah, sure.
So just because I think, to be able to have the discussion, can you explain exactly, kind of, because not everybody here is an expert, right? What it means, strain sensitivity per root hertz.
It's all noise are spectral densities. These are spectral densities. So if I go back to
the per square root hertz means kind of per square root of frequency bandwidth.
Yes. So it would be strain squared per hertz if it was power. So it's just like you measure on a spectrum analyzer. So if I got in a spectrum analyzer and I can measure volts, right? Or I can press a button and measure volts per root hertz. No matter what my bandwidth is, if I press the button for per root hertz, I'll get the same thing. If I press the button for volts, I won't, right? If I'm measuring some noise or some, and then you have this resolution bandwidth that goes between the two, a resolution bandwidth which your spectrum analyzer you must know if you want to convert between the two, but the spectrum analyzer does it for you, okay?
Can you also say a few words? So I understand that this noise spectral density, that's a very useful quantity when comparing to a stochastic signal. But how do I use this if I want to know the sensitivity to a monochromatic gravity?
I'm going to talk about it.
Thank you.
Yeah. That's why I'm doing this, because we have a gravity wave detector. We've got papers where we look in a bar where we look for monochromatic signals. We've got papers where we look for bursts, not stochastic background because you need to tune them to the same frequency. But I'll touch on that too. In my thesis, that's the wrong thing. In my thesis, I came up with this way from the spectral sensitivity, to get the bandwidth. So all you do is this: you find the place where this is minimum, which is here and here, and if you do this integral, you can derive the bandwidth. So if I split this here and I do this integral, I'll come up with the bandwidth. So we can define the bandwidth for some narrow band detector. But so the bars were configured to measure bursts in the solar system. So a typical supernova burst was going to be 1 millisecond. And if you have a 1 millisecond burst, its frequency will be a kilohertz, and the signal's frequency component would be a kilohertz wide. So maybe you go from 500 to 1.5 kilohertz, and you'll get something like this. This is just a diagram. You get the signal will have a width, and will have a center frequency, and that's when you have a signal. This signal is now not noise, so it has different units. This is in strain per hertz. Okay, so how much strain per hertz of frequency have you got in this signal? So if we have LIGO, which is broadband, and we have a signal like this, let's just say it's constant. The strain per hertz comes in. We know the bandwidth. We can calculate the strain from this equation. Okay, that's what you find out when you do the calculation. If the bandwidth is less, you get a suppression by the detector bandwidth, and you can do this calculation. So that's because this won't pick up. Some of the signal will be suppressed in between the humps. Okay. So, and this was the question that was asked, right? What can we detect?
Can I ask a very naive theorist question?
Sure.
So you don't actually find out what is the width of the signal and what is the amplitude. You just get kind of the box. Or?
Yeah. So what a narrowband detector does, it detects the strain per hertz.
Yeah.
Okay. It doesn't detect the strain. So you need to know what that signal width is to work out what the strain is, and you might not know that if you get a burst. So there might be, if you've got more than one detector at different frequencies, you might be able to work it out. Yeah. So you need to. If I don't know what that signal width is, I can't work out what the strain on the detector was. Yeah.
If the signal is narrower than your detector, then presumably you can resolve it.
Yeah, that's what I'm about to say.
Yeah, so like it'll depend on your digitizer.
Yeah. So that's exactly what I'm going to say now. So this is what gravity wave signals can we detect with a resonant mass detector? Well, burst detection, you want to make this width wide. It's important to make this width as wide as possible. And that's what back in the day, because we were going to detect a supernova in the galaxy, which didn't happen when they were running, so we never detected anything. That was the most important thing, so people were trying to figure out how to do that. We can search for pulsars, but you want that to be in your minimum. If I'm searching in the middle here, I've got less sensitivity. I can still do it, but you want to be here.
Sorry, can I interrupt again?
Yeah. Yeah, sure.
So here, when you show a plot like that, right, strain per root hertz, is there any time integration that has gone in there already? So that's the instantaneous
Yeah, so
noise.
what it is, I will show when I talk about axion detectors, when I show some of them, I'll define that better. I know I haven't done that. So all that there is in this figure is the transductance from strain to whatever observable say if I'm measuring voltage, you've got some transductance, which might be a function of frequency, from your gravity wave strain to your voltage. And then the spectral density of voltage noise in your experiment is in that as well. So that's it.
But it's instantaneous. So that would kind of...
Yeah, well,
if you do the same measurement...
It's like a noise. It's got an average value.
Yeah, okay.
Yeah.
Just maybe it's just the time integration for 1 second. That's strain per root hertz. Is you wait 1 second and you see what's the noise. So if you want to integrate for longer time, like the noise scales as square root of time, so then you get the amplitude of a coherent signal if it stays there, or whatever noise that was integrated. So take strain per square root of hertz. I understand it as you wait for 1 second and see.
Yeah, but that's only a fluke, and that's because hertz has inverse units of seconds.
Now I'm confused, right? Because I can either think it is per unit of time, right, and then I integrate for 1 second, or I can think it is per unit of frequency bandwidth, and that.
Yeah, I'm just saying it's
that's
a fluke.
not the same.
It's a fluke, so you don't have to have that way of thinking, but you can. It's only because the unit of hertz is an inverse second that that's true. If a hertz was input 2 seconds, then it'll be 2
Anyway,
seconds.
to reproduce this noise plot, you need to wait for some time. You can't just have it instantaneous there. So you
Yeah.
need to acquire for 1 second to be able to
Or,
reproduce
I mean,
data.
I think the integration time to actually, if you were to measure the noise in your detector, that's a very complicated question, you know. So to measure a plot like this, instantaneous is badly defined. You know, the spectrum analyzer is going, so your lowest frequency number on that plot is 890 hertz, right? So you can ask the question, what is the distance between 2 points on that plot? So the 2 points on that plot are maybe separated by, I don't know, let's make up a number, 5 hertz. Then your spectrum analyzer needs to measure for 1/5 hertz to have, for the FFT to have a resolution of 5 hertz, right? So it's not instantaneous. The spectrum analyzer had to measure for 200 milliseconds. And that's not even all of it, right? So one such measurement would take 200 milliseconds. But the spectrum analyzer, there's statistical noise. So each 200 millisecond, if you just took that one 200 millisecond noise plot, this curve would be very thick. So there would be noise on the noise measurement. So to lower the noise on the noise measurement, you actually average the noise measurement for 50 or 100 averages. So then you end up measuring for 200 milliseconds times 50 or 100, depending on how many averages you did. Does that make sense?
That makes a lot of sense, right? So which basically means that for me to kind of fully understand that plot, you would need to also kind of pass me the information how long you've kind of averaged, right? So that I can kind of
No, because when you measure a level of noise, it's averaging to a certain value.
right, but I need to know for how long you've averaged, right? Because
No.
So what we need to tell you is the frequency resolution of this measurement. And if you know the frequency resolution of the measurement, then you can convert this to strain.
What you'll get is, let's see all this little noise on here. If that will just make that smoother.
right, but that's important, right?
No.
Because
That's just statistical from the measurement device.
This is just characterizing the instrument.
I think what you're asking, Valerie, is I think this curve, in that sense, doesn't have an error bar, but if you knew how long the measurement was taken, then that curve would have error bars, right? Is that what you're referring to?
well, I'm thinking if you pass me a plot like that and you've done less averaging time, right? So it has lots of wobbles on top, right? Then I might draw the conclusion that my signal, which has a certain strain, cannot be measured, right? Because it's within the wobbles of your curve, right?
Yeah, so I think basically what it will depend on is what you're doing with that noise curve, right? So that's where the chapter 2 of the review, right? So if you're trying to measure stochastic gravitational waves, then your limits are coming from this noise curve, then you need to know the answers to those questions. And maybe, I think even then you can say that LIGO measured for 1 year and you take all the FFTs we typically divide up the LIGO data in many segments, right? So we'll take one day of data, and then 1 day of data gets divided into 10,000 segments of each of 1 second or something like that. And then you say each 1 second I FFT and I average it down over 10,000 averages or something. And then you get one noise curve from all of 1 year of LIGO data, right? And that noise curve then you can use to put limits. And so then your observation time and your segmentation time, all of those are indeed used to actually use that noise curve to put limits on actual astrophysical things. Yes, absolutely.
Yeah. This is just characterizing the instrument. Yeah, there's no. Yeah.
I'm not sure if it's maybe a related question, but if I had a short monochromatic signal that's, say, you only see 100 wiggles, so it lasts for 0.1 second, I guess, at this frequency.
Yeah. So generally, what you do is you do.
How do I read off from this plot whether I can detect it or not?
You don't. What we've got to remember is that these plots are to compare sensitivities across detectors. As soon as you start asking questions about source, you can convert and rescale these based on your source.
Yeah.
But the question we're trying to answer is how do we compare these different experiments? This is the way to do it completely independent of what source you're looking for.
So let me say that in another way. So we know what the signal is. It might be a chirp, right? So we have to. So when you do an optimum filter, I left that out. I was going to put it in, but I left it out. You have to match. You have to take your the shape of your signal divided by the noise. Then the complex conjugate of that is your optimum filter, which will give you the best sensitivity. And that's what a template is. So if you know what it is, you can work out the template from knowing the spectral the frequency spectrum of your noise and what the signal looks like. And that's so if I'm doing that for LIGO is pretty broadband, so we don't have to worry about much what the noise is doing. But if I'm doing it for a bar or something that's narrowband, you have to worry about that transfer function and put that in your filter. So it's all optimum filter theory. It was developed in radar a long time ago, which is the same stuff.
Does that mean that signal-to-noise ratio in LIGO would be very different from your signal-to-noise ratio in your experiment?
It depends on the signal. If the signal is, and that's what it's saying here, if the signal was a burst, it would be very different because LIGO would get more of the signal. We would only get it at these points, right? If it was a pulsar and we were lucky enough to be at the bottom here, then there'll be no difference. Yeah.
Does that mean comparing in this way can undersell one detector compared to another when looking for particular sources? Or?
You've just got to understand the physics behind what this means, right? But when you do these plots, you're not saying anything about sources. But a theorist should be able to grab the plots and work out what the sensitivity is to their source of interest from that data.
I think, in other words, to answer your question, Jermaine, like if you knew the frequency of your signal, you should build a resonant detector that can get as deep as possible at that frequency. But if you don't know the frequency of that signal, then it sort of becomes do you build a resonant detector that's very sensitive at one frequency, or do you build a broadband detector that's not so sensitive at that frequency?
That's a problem with axions too, right?
Yes, exactly.
Yeah.
Yeah, just to make it a bit more clear, because so suppose that you have an event or a continuous signal at 920 hertz, and the magnitude is 10 to minus 20. You can resolve it within 1 second of time integration.
Yes.
Everyone agrees? Okay, now let's make another example. Suppose that the magnitude is 10 to minus 23. You can't resolve it in
You've got to
one time.
average.
You need to average that. That dip will go down the square root of time.
Absolutely.
So
that's something about the signal.
Yeah, that's how you read
no. This is just to recover. Just to see
Yeah.
if someone wants to read a plot.
Exactly.
Where is my signal and where is my sensitivity curve? For a broadband signal, you will have it everywhere in the frequency spectrum. So you need to integrate in the frequency domain.
Mm-hmm.
And when you integrate in the frequency domain, you see that there are regions that have less sensitivity, regions that are more sensitive. LIGO for a broadband signal has a sensitivity that is almost somehow constant with respect to this in all the frequency region where it.
In other words, when you're looking for a source, the way you do your data retrieval and analysis could be totally different. And that comes out in axions too. With ADMX, they look for the galactic halo, which is just a narrowband noise source. In the communication theory, the galactic halo is just a narrowband noise source of a part in 10 to the 6 width. And that's been developed all in communication theories. But if you're looking for a cold flow from the galaxy, then that is totally different. It's got Doppler shifts, and you look for it differently. And my student's been involved in that with ADMX doing the high-res analysis. And it's very interesting to see the difference between the two analyses. Yeah.
So that was super useful for me, the way you phrased that, right? I'd like that sentence. So kind of how to read this plot.
Yeah.
But just to follow up, so if basically the sensitivity is given as per root hertz, right? It really means
1 second integration
Yes.
for every single frequency bin.
right, but it means I can assume that kind of with time, this really scales as 1 over square root of
This is
the integration
statistical.
time. So it's statistically limited, and
Yes.
and
Yes.
I can kind of just
Yes.
Yeah.
assuming my source lasts long enough,
Yes.
I can just
Yeah.
rescale
Yeah.
in that
If
way.
your source is, the integration
Yeah.
physics should be really thought of as signal is integrating in my detector, and the noise will stay constant at this per root hertz level. It can depend on the noise. So what I was saying earlier, if it was like statistical noise from the spectrum analyzer, that you can average down, and maybe after like 50 averages, we give you this plot. And when we give you this plot, it's saying that we've done maximum number of averages, and sort of it's not going to go down much below this, right? So that at that point, you start to need to integrate more to develop more signal, or to integrate more signal power into your measurement. Does that?
You could have, there can be systematics buried in your noise too, which stops you integrating down.
Yeah, exactly. And so that's at the level at which you would publish this plot.
Yeah, so this is just noise, That's all it is. It's just it's just referred to back to the input. That's as simple as that. It's just like what lots of people do in lots of different forms of experiments. So now stochastic background, that came up. So if we really want to know the stochastic background, we need 2 detectors at least to do a coincidence analysis. And it's better to be broadband, I guess. I don't know. I haven't thought much about statistics. So we thought about this a lot in the past, and there was a way to get that down. So Niobe looked like this before it was hit on the head because of the interferometers, but we had a plan to get down to here. So the difference was that this is 4 Kelvin and low electromechanical coupling between the mode and the photons that were reading it out. And this was a high coupling with 3 modes detector at 25 millikelvin. And we had a program to do this. And there was going to be a big sphere built at NICEF, and we were going to do all the transducers. And I don't know if anyone remembers anything about that, but I was pretty excited about that. We're going to cool to the ground state and everything. So let me just take you through one process to get to that sensitivity on a bar. So if we're looking for a burst, we will read out that displacement. There's 2 quadrants in the displacement. And so the bar has got a peak, and this is the sort of the lock-in amplifier centered on the 2 resonant peaks. And we look at the difference. We take a subtraction of your next sampling time. We subtract away. So this might be some average, and this might be some average, but they're separated by a time, and it's that difference that we look at. So if we're looking for an impulse, we're trying to see it when this moves 1 step along this phase plane. This is our detector, what it looked like in the day. And when you plot x and y squared, you get the mode temperature. Okay? And we were actually cold damp. There was talk about cooling. Because it's a parametric transducer, we cooled this. We cold damp from, I can show you the plot here. So when you've got a microwave source you're increasing the power on to get better sensitivity, because the higher power, the better sensitivity you can get on your displacement measurement. But as you put high power, if it's below resonance, you cool the system through this cooling mechanism, parametric cooling. And so we cooled ours from a few by 10 to the 7 of the 2 modes down to nearly 10 to the 4. We could cool it by putting much power. The problem was that amplitude noise would then act back on the system, and it looked like thermal noise, and it would go up. So this was an optimization process, so we had to pick a power before that occurred. But we knew how to make our sources more low AM noise, so that could have been pushed out if we had a chance to improve this. So there's a whole bunch of noise sources, and you can sum them up as narrowband and broadband. But when your transducer is kicking this, it excites it like a thermal noise, and it's narrowband, and it looks. And so we showed that. We showed this operated in this cold damp regime. It was a bit before its time, and these measurements could be done much more quickly than the ring down time, so you'd get some filtering. And when we look at what we were reading out, this difference as a function of, and we could turn that into a temperature, there was an optimum integration bandwidth or sampling time, the inverse of this delta t. And that's the same as an optimum filter. This is called zero-order predictor, and that was an optimum filter. And so when you look at the histograms of that difference, these temperatures are much smaller. So our effective temperature is on the order of millikelvin. All right, so that's how we can get, but that's only relevant for a burst, a burst in this case. But that's how we can get the full sensitivity. And the reason you get a much lower noise temperature is because your Q, our resonators had a Q of, they were 700 hertz. Originally it was 2 by 10 to the 8, but we cold damped to 10 to the 6. A ring down time of 450 seconds, but our sampling time was only 1 second. So we got this suppression from the mode temperature to the effective temperature. So we could resolve energy events. See, this resolving of these events out here was much more precise than the actual temperature. So that's what an optimum filter does. This is effectively an optimum filter for a burst. Okay, we're filtering into the noise, and we're getting a much better sensitivity. So that's what we do when we do a template. So if it's some ringing thing, our template is doing the same thing. It's bearing down into the noise just like this is, but this is for a burst. So this process of what you're doing to bury down to the noise with a template is different for every noise source you're looking for. Yeah.
When you do parametric feedback, is it feedback cooling? So do you also use the phase information?
It's not feedback cooling. It's the fact that it's optomechanics. Okay. Yeah. So when you get your two side bands, when you're on resonance, nothing happens. When you go below resonance, you get you damp it. When you're above resonance, you excite it. So this is so the new wave of optomechanics is just doing this, but we were doing it in a bar way before everyone else, before these optomechanics became trendy. Yeah. All the other resonant bar detectors were using squids, and they weren't parametric. Ours was the only one that used this parametric transducer. So that was very interesting. That's how we did our optimum filter. And this shows you the effect of cold damping. So this is if you're on resonance, you don't change the Q. When you take your microwave mode below the resonance of your transducer, you get this. You damp the oscillators, but you also cool it. So Q on T remains constant. Here's an example of 10 to the 6 cooling to 10 to the 5. So we were trying to get to this standard quantum limit, and so I just put this up because I think it's interesting, because some of you guys are building detectors and you might want to try these things, you know. We had a bath temperature of 5 Kelvin, so that means the number of phonons at 700 hertz was 10 to the 8. So from the bath, we had 10 to the 8 phonons. But then we parametrically cold damp. You could call it cooling, but we called it cold damping then. But if you call it cooling, you forget that it damps as well. The new wave of optomechanics, people were thinking they could cool and have the same Q. When we did that, we reduced, because we cooled, we reduced the number of phonons to 8 by 10 to the 6. Okay? Then what we do in our filtering, because of the high Q and we're measuring much more quickly, you hasn't got time to get the RMS average. So we're basically measuring a change. We're sensitive to a change in phonons of 10 to the 4. So even though our bath is 8 by 10 to the 6, because we're doing this difference, we can measure a signal that generates the noise is on the 10 to the 4 phonons. So if our strain is puts greater than 10 to the 4 phonons in our detector, we can measure it. Okay. And to get to this standard quantum limit was when I first became a postdoc. I said, what do I want to do? I want to cool and get to the standard quantum limit and go below. That was my goal. But it never happens. Other people did it, but it was good to have a goal. So this is, if your effective temperature is greater than 0.5 microkelvin, you're above the standard quantum limit. You have to get below. And then when you get at the standard quantum limit, you could do all your quantum metrology protocols like QND measurements and stuff. So the high Q lets you get to the standard quantum limit at a higher bath temperature for these experiments. So now, so this is what we're doing now, as you all saw. And then you can see that we know our the thing about MAGE is we can see the thermal noise much clearer than we could Niobe, so it wasn't as thin, and so it's quite looks quite good. So now if I get to we come to axions, and the interesting thing is now we have the same situation with axions because they're gravity wave detectors, but I believe all this way of thinking can be transferred to the axion domain as well, and it should. This way of thinking in spectral sensitivity. People who do axion detectors should plot their spectral sensitivity of their detector. I believe they should.
And what do they currently plot?
Because everyone knows what their signal is, that's a galactic halo, which is a narrowband. I'm going to get into that.
Or they just plot the G.
Yeah, that's right. And that can have a lot of assumptions. But it's all got the same signal. The signal is narrowband noise. If you do communicate, I did electrical engineering degree too, to do communications theory. It's just a narrowband noise source. So we've got organ, we've got upload, which is which has got two modes in one cavity, and we've got this new one called this anion detector. I won't go into that. It's like a version of upload, but with one mode. And organ, which is two papers are coming out, one accepted in PRL and one in PRD. And with ADMX, they've just put this on the archive, non-virialized axion search, which is sensitive to Doppler effects. So this is a totally different way of analyzing the data here, because we're looking for coherent sources that have Doppler effects coming from the Milky Way. Okay. So this paper I wrote, as soon as all this gravity wave paper came out, that there's some people who are authors in the audience, which I think is a great paper. I loved it. I just started thinking, we should start thinking of this way with the bars and with how the bars and the interferometers, the same as that challenge, We had all the bars were trying to stay afloat and keep going. You've got an experiment, you don't want to destroy it, it's really fun. You want to cool to the ground state, you want to get funding, but interferometers come in and take over. And now in axions, we've got so many different experiments. It can't last forever, all these different experiments. Eventually it will probably just, so we've probably got to, but this paper was a way we could look at all the experiments we're doing in the lab and compare them on one figure. So we have this effect, which has been discussed many times. So here we go into axions. Axions have this narrowband noise signal. And that's because the galactic halo is virialized, and so it spreads out. And so you can approximate it as this narrowband noise source. It's got a width. And if we just look at it as this theta, which is G times A, we've got a dimensionless parameter that we can work on. And this axion source is actually can be written down in theta squared per hertz because it's a narrowband noise source. So you can write it down in spectral form. It's noise, okay? That's what it is.
Here theta is a theta QCD, or?
No, it's just G times A. So A is your axion field, so that's your field strength, and G is your coupling. Okay.
This is so A over FA would be the theta of QCD, so this G is then, so it's not an angle, but it's dimensionless quantity.
Yeah.
It's a dimensionless quantity, and that's what people write down, so I'm just copying. As an experimentalist, we let the theorists worry about what they mean, we just try. So it's very unlikely that a gravitational wave signal will be of this same form. So you can't use these axion limits to put gravitational limits. You've got to work out your sources and all that, And so we can calculate spectral sensitivity in terms of this theta, I call it theta A as well. And that's what we should do because we just found from that paper that was published that theta is on the same order of the strain in your detector. So, and then I'll make the statement here again that cold flows are more coherent, so it's a different way of analysing the data. So here we go back to the theory. We've got this theta and this, I called it theta naught here, but anyway, this average value of this is just some integral over some spectrum, and where this spectrum has the units 1 on hertz, and if we take the square root of that, that's 1 on root hertz. So that's like strain per root hertz. Okay, strain has got no units; it's per root hertz, and we know strain is on the same order of this, so we can put everything on the one figure. So that's what I liked about it. So I went on a mission to try and do this with the help of everyone in the group, and so now we've got our usual thing. If you know axions, you know that this theta naught is related to the dark matter density around us. If this narrowband noise source of this narrow, and you can work out what this theta A is, but this is a field. It doesn't have, but if we want this, we have to include. It has to be G times A to do the spectral sensitivity. So there's two things you try and do in an experiment. You have an observable, and there's some function that relates you to this. What you're trying to measure, and this is the observable you're measuring. It could be voltage, could be power, whatever your experiment is measuring. And you've got this conversion between the two, and I call this a transductance because it's just a transductance because you're transducing this to your observable. And so we want to know. As an experimentalist, I want to maximize this, and I want to minimize any noise in my system, so I can measure this. That's the goal. And so the signal the signal that we're seeing here in my observable units is just this squared times this. And if you want to do it in terms of the axion field, you have to put this GA gamma gamma squared there. But that's not unitless anymore, so I can't really compare that to gravity wave detectors. Okay. Spectral density of axion detectors. So you want to minimize noise sources. We've gone through this. This is when I do consider the noise is a narrow band, I get this equation of the signal to noise ratio. And now I've got this integration time. So how I average, and you'll find that you've got this so this will average. If your time is less than this, you get t to the half. If your time of averaging is greater than this, you get a reduced sensitivity because it's got a spread and you can't average into that spread of energy. You start to lose signal. So this comes from Dickey radiometer equation.
What is delta F here?
It's a bandwidth.
Of the source?
Yeah, it's of your measurement time.
So delta F is same as delta FA?
Oh, sorry, delta FA is your axion width.
Bandwidth.
Yeah.
And delta F is the resolution bandwidth of your detector?
Delta FA is the delta F is the that should be delta FA probably. That should be delta FA.
So this is all the bandwidth of the signal.
Yes, that should be delta FA.
And this does not take into account how you chop up the data. So if you took data for 2 years and you had to chop it up into segments of 1 second and you FFT'd each of those segments, this does not take that into account. This is just the T here is just that 1 year.
Yes.
But I think because you write it this way, you must be making some assumption. You must be assuming that your each segment is 1 over delta FA.
Yes. Well, here you're assuming
because that's the optimal way to chop up the data.
That's right. Yes, I agree with you. Yeah,
okay.
Yeah, I agree with you.
Mike, we should try to wrap up in 5 minutes.
Yeah. Okay.
Not to eat too much into
Yes. No, we can wrap up. I'm nearly finished. So what you see here in this signal to noise ratio is the spectral density here. you see. So there was a question of how to use the spectral density here, and there was also the point that's at 1 second, so I put 1 second here. Yeah, that's right. Okay. So the spectral density is in this formula, you see. Anyway, I don't want to go through all this. I will just skip through this. If you're interested in the paper, I've done it for abracadabra. I've looked at the noise sources. I've worked out the spectral sensitivities. I've done it for shaft. I've done it for resonant haloscopes. And see, here's ADMX. Here's it as in terms of power, watts per hertz. And you could, so this is the spectral density of noise in the cavity, and that's your amplifier noise. And you can see a little dip here. If you can move if you can get a better amplifier noise, you get a bigger dip. And you can do all the same calculation, and this you can then convert into a per root hertz as well. And so that's what we did, and this looks like...
Wait, sorry, can I...
Yeah?
Can I interrupt there? Because, I mean, I know for the Abra case, right? I mean, I know that it really... It depends a lot on, like, if I want to use that plot, right? So if I have a certain source in mind, I know it depends a lot on how the duration of the source compares to the different timescale of the cavity. Because the scaling with time is different depending in which part of this, like exactly the same as for axions,
yes.
right?
Yes.
So how is that information now encoded in a single curve? That seems magic.
It's exactly the same as the interferometers to bars question. One's broadband and one's narrowband. There's nothing different.
No, there is something different because I'm just talking about a single experiment, right? Just take abracadabra. But then if I want to kind of understand kind of how the SNR grows with time, it depends on which... that there's not a uniform answer to that, right? Exactly the same as for the axions, right? It depends on kind of how the timescale of your source relates to the different timescales of the cavity. You have different regimes, right? Where you get different scaling with time, t to 1/2, t to 1/4.
What do you mean by timescale of the cavity?
Well, okay. I mean, things like kind of, okay, now I'm mixing a bit the haloscopes with the SRF cavities, but like things like the ring up time of the cavity, the quality inverse of the quality factor. I mean, basically all the inverse of all the quality factors involved, right? Be it the cavity, be it the LC circuit. I mean, all these timescales matter, right? And you don't get a uniform answer across all those timescales.
Yeah, but you can plot the spectral sensitivity.
Right, but I don't know how to use it. This is my problem.
No, yes, but
if I can just interject at this point.
Yes.
So I think that the point of using sort of strain per root hertz is that it's a very useful tool for comparing different experiments with each other in a sort of apples to apples way, like Mike is suggesting. However, I wouldn't necessarily recommend using strain per root hertz, this figure of merit, to then try and calculate your sensitivity to a particular signal. Instead, if you have a particular signal in mind with a particular spectral form, you can just integrate it directly into your SNR and compute your sensitivity to a particular strain. Right? So rather than try and use this and then figure out which timescale goes in where, how, etc., it's easier just to say, if I assume a particular signal, then I can just calculate SNR straightforwardly.
Yes. Yeah. But it is in there. But you would...
It's definitely in there, but it's complicated to then, figure out for a particular experiment, like Valerie's saying. Sometimes there can be 2, 3, or even more timescales in the problem, and figuring out exactly which regime you're in requires a careful analysis.
Yeah, so...
At which point you may as well just do the analysis.
You can do the optimum filter, and that's just knowing the noise and the signal. But if you don't know the signal, then you're just looking, then you don't know, and yeah, that's different.
Yeah, just can I say something, because there were mentioned 2 times. One is the time of the cavity that Valerie was mentioning, and what if the signal has a time that is smaller than the ring up time of the cavity? So you have to compute whatever sensitivity is computed for duration of the signal at the time of the cavity or bigger. And then you compute the sensitivity based on that quality factor. If the signal is smaller than the ring up cavity time, then you don't have the right picture. So you have to compute another sensitivity based on another cavity quality factor, which is reduced because the signal has shorter duration.
I wouldn't say that the quality factor is reduced. It's just a different calculation, right?
Yeah,
the quality factor is
Yeah,
something
but
intrinsic to your cavity.
Yeah, it's not the quality factor that is reduced. It's just the signal has a lower duration time, and you have to scale the sensitivity with another type of quality factor.
I have a proposal. So we did this very recently for one of the primordial black hole analysis in LIGO, where the duration of the primordial black hole signal could be shorter than the duration of the observation time of LIGO. So you need to take that into account. And it's the same thing here. The quality factor, if the cavity ring up time is much higher than the duration of the signal, so you just define a t, and then you define that t saying it is the minimum of the 2 times. So you take your t, the t that you use in these equations, you just redefine that t not as the cavity line width or as the observation time or as the signal duration. You say this t is the minimum of these 3 quantities. And that's really how you should do this. And I think I agree with Sebastian that comparing SNRs is better, but then you get into the problem of as soon as you have a new source on the table, that plot goes out the window. Your detectors, you can't just use that SNR plot to then compare the detectors for a different source.
Right, exactly. So that's the whole point, is that the strain per root hertz is a good comparison tool, but an SNR is for a given source how you would compute the sensitivity of a given detector.
And it's just like what I've been trying to show here. When you got a different signal, you use different techniques to process that. And that's in ADMX, they're doing that when they look for coherent flows and the galactic background, but they're using the same data, they're analyzing it in a different way, and they get different couplings to GA gamma gamma because they're totally different, right? But if you're trying to look, there's so much you look at all these detectors and they're very hard to know or to compare when you're just seeing plots of GA gamma gamma because you don't know how long they've looked for, you don't know what they've assumed. But if you plot the spectral sensitivity, it doesn't lie. And this is in this paper, this is the figure. You've got LIGO, this is the strain per root hertz or theta or whatever you call it per root hertz. And we've got our experiments there, all our experiments, MAGE, I can compare MAGE, organ, and upload. And then we've got Abra and Shaft and LIGO, all on the one figure.
Okay, so I think this was your last slide,
Yeah,
right?
it's last slide. Yeah.
So since it's already time for the coffee break, if there's still one more urgent question, we can maybe take it now. Otherwise, I would propose that we continue the discussion in the afternoon where we still have time. And then I would really propose that we have a discussion on, well, of course, how to compare experimental performance. You've already given us now all the material we need for that. But with specific focus to the white paper, I think we need both a discussion on how we compare this at the level of comparing experiments, but also at the level of how to compare sensitivity to specific sources. So I think for the white paper, the goal should be that both it gives a fair comparison to the detector community, but on the other hand, it enables the source community to figure out how sensitive a particular experiment is going to be to their favorite source without having to know the nitty-gritty details of every single experiment and having to go through the full calculation of the SNR for every single experiment. And how to achieve that, if it can at all be achieved, I think that is something we should discuss in the afternoon.
I think I agree. Yeah, I would like to add I would like to add one more material that is not here yet. So I think in the S theta comparison, there is still an assumption of axion experiments that are relying on the cosmic density of axions.
Oh, you don't have...
because
there's no cosmic density in there. There's nothing.
No, you have factored it out, but it's still, you can't write S theta for experiments that don't look for cosmic axions, can you?
Well, you can, yes.
Okay, then that's what we should do, because...
in ADMX, we look for...
you look for dark matter sourcing the axions, right? Your A is arrived from rho
I was about to say
dm.
what I was going to say. We're looking for cold flows from the center of the galaxy. We can do that, and we can look for virialized axions. They're totally different You're coming from totally different
But
sources.
you're not producing them in the lab. So I'm
No.
saying that the lab-produced axions
The lab
should-
produced axions.
that they are not going to be included in this description. So if we can find an axion plot that can also...
I haven't thought about the lab produced.
Yeah, exactly. So I
axions.
think it's not a unifying picture just yet.
Because you've got to produce and detect.
Yes.
That's a different story.
Okay, is the comment so urgent that it can wait? That it can't wait until the afternoon?
No, it was just a really few words, just a quick comment, and just to enhance that what Valerie mentioned, the importance of the ratios between the time scale of the signal and the different time scale that enters into the detector. It's not a small effect. It is something that is really, really important. It's of high importance. If it's not clear for everyone in the audience, this is something that mustn't be neglected at all. Just to say that.
Okay.
I would like to add that we're going to discuss this on Friday.
You really don't want to have coffee, right?
I will talk about that on Friday.